And I think I remember you telling this story. Some of this kind of became a little bit more clear to you because you were using cancer cells in petri dish with different metabolites and noticing something interesting was happening with the cancer cells. And I believe it was beta hydroxybutyrate, correct? That you were
Yeah.
not necessarily expecting.
Yeah. I think going back to my early studies, and I have to think about the dates. I think it was like 2007 or 8, where we had cancer cells, U87 MG cells, which are like a glioblastoma cell line. I think originally derived from like a 44-year-old glioblastoma patient, right? And I had them back from my postdoctoral fellowship in Ohio and brought them down to Florida, where I was doing my postdoctoral training. And I had access to medical students who wanted to do some research. So I would grow them in culture in petri dishes, and I would have the medical students do little projects. And they didn't really know what they were giving them. Like I didn't tell them. I was like, give them molecule, this molecule X and molecule Z or whatever, and treat them at different concentrations. And we were using some molecules that were, I want to actually revisit, like 2-deoxyglucose and lonidamine, and they're glycolytic inhibitors. And then we started, I was focused on that first, but then actually got beta hydroxybutyrate and started growing the cancer cells in the absence and the presence of the ketone beta hydroxybutyrate at levels that we could achieve with the ketogenic diet or supplementation. And noticed that the cancer cells were not growing as well, and it was decreasing their proliferation. We would do like a proliferation assay. And then it was also, we did a live cell death assay, and we noticed there were less live cells and more dead cells when we grew these cancer cells in the presence of ketones, and we kept glucose normal. So we didn't even like alter the glucose levels. So that was one observation. And we also we grew like human fibroblasts and neurons, and then we would lower the glucose and elevate the ketones. And in that context, the brain cancer cells and the human dermal fibroblasts were perfectly happy and healthy. But when we lowered the glucose and elevated the ketones in cancer cells, like all the cancer cells died. So this was like a visual representation of kind of what was going on, that there was, that cancer cells could not survive in the absence of glucose or the lowering of glucose. So we kept it just at a low level. And that the cancer cells really lack the metabolic flexibility to transition to using glucose to using to using ketones. So they had a very high glycolytic need for growth and repair. So the cancer cells use glucose for energy, but they also use it to expand, to basically as to make to for the expanding biomass of the tumor. So as the cells divide, the glucose is shuttled into, for example, lipids. So you have to make a lot of membrane, as cells are dividing and replicating. And a large majority of the glucose actually goes towards that. It's also used for energy. So the ketones, some cancer cells can use ketones. Uh, if you do tracer studies, which called tracer studies, you can actually see that the carbons from the ketones can be used in the expanding biomass of the tumor. But if you have a very aggressive cancer line, they have altered mitochondria, and it's altered in a way, there's structural and functional alterations in the mitochondria that prevent the cancer cells from efficiently using ketones as an energy source, but they can use them for biosynthetic processes. And that's where there's a lot of like a bit of confusion that, I get asked the questions, can cancer cells use ketones? And I think that the large, the large majority of cancer cells can actually probably use it for energetic processes, but it's not a very efficient fuel. But they can be shuttled into lipid biosynthesis to contribute to the expanding biomass of the tumor. So that could be acknowledged. But from my understanding, there are no cancer cells. If you subtract glucose and glutamine, it'll essentially kill all cancer cells. I don't think any cancer cells can survive in if you lower glucose and glutamine. Whereas, we work with a variety of different cell lines, smooth muscle cells, human dermal fibroblast cell, like a variety of different cell lines do remarkably well. if you dramatically lower glucose and glutamine, and they do really well. But cancer cells will quickly die. I mean, this is pretty much any cancer cell you look at, and that's that's something that cancer biologists are not focusing enough on. And I think a lot more time, energy, and experimentation needs to be directed towards metabolically managing cancer from the context of using glycolytic inhibitors and inhibiting glutamine metabolism or glutaminolysis in tumors. I think there's tremendous potential to strategically metabolically inhibit, and that may not be, it's probably not a standalone therapy to use it, but it could further augment the therapeutic efficacy of the standard of care. That could be radiation, chemo, and even immune-based therapies like checkpoint inhibitors. I think there's great synergy with therapeutic ketosis and targeting glutamine, for example, with PD-1 inhibitors.
Interesting. Yeah, well, I would love to see that research done as well. But it's like Dr. Thomas Seyfried told us on the show, like cancer is a revenue-creating disease. And so it's going to be hard to be really motivated to fund some of this research, right? Like that's going to be tough.
Yeah, that is true. And you do see that, he brought that up early on. We started communicating well over a decade ago. And there's a lot of truth to that, but there's also truth to like, working with different cancer organizations that are funded by pharma, and even we collaborate with the Moffitt Cancer Center here, and it is a cancer industry. I mean, it makes money. It exists because of the standard of care that's being utilized, and many cancers do respond remarkably well to the standard of care, especially and so Tom Seifert and our lab focus on cancers that are essentially resistant to the standard of care. So that would include glioblastoma, even low-grade glioma, and stage 4 metastatic cancer. It's like, the standard of care doesn't work for them. So we focus all our time and energy on advanced aggressive brain cancer models, and also metastatic cancer. There are many scientists who study cancer and or different tumors, like patient-derived xenografts, for example, or cancer cells in a petri dish. But all cancer researchers should really be studying metastatic cancer, and very few cancer researchers study metastatic cancer because you don't die of a tumor, unless it's a brain tumor. But even in that case, you got metastasis, and it infiltrates different areas, so it spreads. But I think the large majority of cancer research should really be focused on developing really good models of metastatic cancer. And Thomas Seyfried has one of the best models of metastatic cancer that I know of, which is the VMM3 model of metastatic cancer. It made like the front cover of the International Journal of Cancer like over a decade ago.
Wow.
In our hands, I mean, this is like the most deadly, fast, aggressive cancer that you could see. Like, you inject the cancer cells into the flank, and then there's rapid spread and metastasis to the brain, to the liver. The liver is like peppered with all these metastatic lesions. It's just like this deadly form of cancer. So it represented to us a great model for us to test the ketogenic diet, and also we've never studied the ketogenic diet as a standalone. So even from right out of the gate, we combine the ketogenic diet with hyperbaric oxygen therapy. So in the context of high pressure oxygen delivered 3 times a week, 2.5 atmospheres for 60 to 90 minutes, you hyperoxygenate the tumor. That massively increases reactive oxygen species. And then in the context of a tumor, you have a lot of free iron. It drives the Fenton reaction. So you have more oxidative stress that's cancer specific, right? So that is a strategy I think needs to be really employed, and that, even in the context of radiation, the efficacy of radiation is proportional to the PO2 of the tumor. So you could utilize oxygen with radiation, and some people are doing that. So there's just so much to unpack. And I guess, when you think about it, ketogenic diets, diet therapies, hyperbaric oxygen, it is difficult for cancer treatment centers and research centers to make money off this. So but we are equally interested in small molecules and various cancer drugs that, because I think there's equally, they could be equally efficacious or more efficacious for managing cancer. And I think they synergize well with a ketogenic diet. The ketogenic diet can enhance your cancer specific immunity. It could help your immune system recognize cancer. Um, it can decrease side effects. It can help the patient throughout their therapy by decreasing side effects. And we think that if you titrate the protein and elevate ketones and sustain ketones, that ketones have an anti-catabolic effect. I mean, from an evolutionary perspective, if we didn't make ketones, we would massively, our skeletal muscle wasting would be so rapid, we would die from muscle wasting. So elevating and sustaining ketone levels throughout cancer therapy, you have the anti-tumor effects, the anti-inflammatory effects, and then the ketones have well-defined anti-catabolic effects. So it helps your body, it lowers the level of alanine. So when we break down muscle, you release a lot of gluconeogenic amino acids like alanine, and these go down. The branched chain amino acids are preserved. So there are very real, benefits to being in therapeutic ketosis throughout standard of care therapies. So I think that needs to be acknowledged and needs to be studied.